Okay, so let's start. Hi everyone. Today we're going to talk about search, specifically about linear search and binary search. So to begin with, what is search? I think that you all are familiar with search. This is a very important concept and feature in many programs, site, and so on. And when you are implementing different algorithms, it is a common problem to find an element by some properties and so on among the huge data set. So we have, and we are going to consider today two types of search, linear and binary. Linear search is less efficient than binary search, and binary search today is used more, especially in very big data sets. So let's start from the linear search. So here you can see an image how linear search works. Basically, it's like traversing through array and comparing element to the key element, and you find it in that way. So for example, if we want to find 23, we are starting from the beginning of our array, and we are going through every element. So here is step-by-step algorithm of realization. We traverse the array, we compare key element with our current array element, and if we found this element, we return its index, and if we don't found it, we return, for example, -1. And question for everybody about time complexity of this algorithm, who knows? Yeah, because the worst case scenario is this element is the last one in our array. Okay, so now code. As you can see, this code is pretty simple. You just go through array and that's all, and compare elements. But here is also a recursive method of linear search. You can see here that you pass the size of an array, and you go from the end of array, and if you don't find the element, you just, you just start this algorithm again, but you move to one element to the left. And that's all. Do you have some questions? Okay, so here I want to tell you something, that yesterday I was curious about recursive method of linear search, and I had a consideration. So if we have 100 millions of elements, I think that our stack will be totally overflowed. Yeah, it will be dead. And also I have calculated this variation of search, not recursive, and recursive method is actually longer, because your system also takes some time to push the element to the stack and to write it from the stack, read it from the stack. So that's why I don't recommend to use recursive methods with linear search, especially if there are a lot of elements, because my stack overflowed yesterday after 1,000 of elements. Yeah, so you should be careful with recursive methods. But that's really interesting to know that you can do it this way. Now let's talk about binary search. Binary search is an algorithm which can be used in sorted lists of data, sorted. And it is a lot more efficient than linear search. So how it works? You can look on this image, but I also can draw. So you have elements, 1, 2, 3, 4, 5, 6, 7, 8, 8 elements. And for example, you want to find this element. If it was a linear search, we would have a complexity ON, because it is the last one. But how works the binary search? So we are finding the middle element. So it will be 8 divided by 2. It is 4. So we divide our array to 2 parts. We look at this middle element. Whether our search element is less or no. If it is less, we are going to this part. If it is higher, we are going to this part. Our element is higher, so we are going to this part. we are finding a middle element again. Now we look at this element. And we're looking whether our search element is more than this, higher than this, or less. It is higher. So we are going again till we have only one element left. And we found this array, or this element in this array. So as you can see, if we have 8 elements, we need only 3 iterations, not 8 as with the linear search. And as you understood, this is true only for sorted lists, with sorted data. So why we need this binary search? The thing is that when our data set increases and we use linear search, its complexity is increased proportionally. So more elements, it will take more time. But in the case of binary search, it also increases, but not proportionally, because the complexity of this is log from n to base 2. I will understand. You can see the graph and the complexity of linear search and binary search. So ON, it is like an average complexity. It is not bad, it is not good, it's average. But binary search is really efficient. It's really efficient. And I will explain how it works. So as you remember, log to base 2 x, for example. So this means in which power we need to put 2 to get x. For example, if we have, as in our example, 8 elements, then in which power we need to raise 2 to get 8, it will be 3. Nice. So as you saw, only 3 iterations. And when the amount of our element grows, this amount grows a little bit. So if we have 16 elements, then we need how many iterations? Yes, and if, I don't know, 256.
Yeah, 10, I think. I just remember 10.
For
Calculating.
I think 10. I think 10. Okay, 8. 8
who told 8 for the first time? Nice. Okay, so is everything clear? Nice, that's great. So let's look on the realization. We also will consider 2 realizations, recursive and not recursive. By the way, in this case, recursive methods is okay, because usually we talked with Sergey, if we have 1 million of elements, it takes like 20 iterations. Well, your stack will be okay. Yeah. So you can use it. And let's look on this realization. So we begin from the beginning. We look on the first element. And our right element is our our last element. Then we are going to do the loop until the place when we will left will be here and right will be here. So we will shorten our array till the point we check all the elements. Do you understand? Yes. So when they equal, we check them again, and then we just go break the loop. Okay. So we are finding the middle element, left plus right divided by 2. We found our middle element, and then we are looking. If this element equals to the search, we found the element. If middle element less than search, then we take left and we move it to the next element from middle. I will draw again.
Our integer search, what does it mean? Integer search.
What do you want to count?
Like the element.
That's the value.
In the head of the class we have
Integer, it's an index of the element.
Like the element you want to count.
Index of the element.
Insert in the head.
Ah, yes. Search is an element, like key element, you know. Okay, so we have 8 elements. Then we are finding middle element. Which one?
For again.
This one, yes? Okay. We found this element. And then okay, imagine that we are looking for this one. Okay, so we're looking at this element, and here, is mid less than search or it is more than search? In our case, it is more than this element. That's why we're doing right equals middle minus 1. That means that now our right element is this. And we will not consider this part anymore. And now we are starting from this and end by this. Now, which is the next middle element? Nice. Now we are here, and we are looking. 3 is more than 1 or less than 1?
We get more.
Nice. So now our element will be this, and this part is not considered by us anymore. And now, what will happen? Again, and yes. So we are completing the search till we have only one element left. And this element will be our key element. So we found it by the index of 0.
Okay, and because we wrote middle mid as integer, we get here we get 0. Like when we find the mid for one element.
Why did we return -1?
We return -1 if these all conditions are false. That means that we didn't find our element. So we return -1 like error, no element.
So I can, for example, replace it with throw no such element exception.
Yeah, sure, yeah.
The -1 is just for the program, not to throw the errors.
What if our array isn't sorted?
You can't use this method. So that's the point. So imagine that you have a shop and you have some items, you have some data set, and you can use linear search to find your items, but it will cost you a lot more than if you will save your items in the sorted order and then apply binary search for them.
Is there a sorting method that sorts or not in the not sorted array?
So I don't think that I don't think that it will be efficient if you will at first sort array and then apply binary search for it. I'm not sure. I think that the key to success is to save in the first place all your items in the sorted order from the beginning.
Yeah.
Yeah.
I guess we can encounter some problem if we have like a large array with many numbers not sorted and we need to find one.
Sure, because you could not use this method binary search and it will be.
I can't use either.
You can.
But it's going to be Stack Overflow.
No, only if you write recursive method function.
Okay.
You can.
If I use liner, it will work, but it will work
Very long.
Yeah, you will go through every element. Imagine you have 1 million elements and you will go one by one for a million times if it is a millionth element. On binary search, you can see this graph. So this is a number of elements and this is the number of iterations. So for example, if we have 8 elements, then we need 3 iterations. Here we need 8 iterations. And if we have 16 elements, we need 4 iterations. Here we need 16 iterations. Okay. So everyone is clear?
You know, you sounded like this life coach when you said like sorting elements is the right thing.
If you want to start a business, remember this. Okay, nice. Thank you for your question. Let's go to the recursive method. So I think it should be easy for you. The same situation, but here you need to pass an array, the key element, the low and high. Low is the element from which we are starting to search, and high it is the last element of our array. When we are running this method, we pass here array search 0 and array size -1, and we are performing the same logic. So first of all, if low is more than high, then we return because we didn't find elements. Remember, like we just cross this middle position. Then you're already familiar with it. If our search element is more than middle, we need to go to this half of array. That's why we're running this method again, but we're starting it from middle +1 till high. Middle +1 is here element, or this element to this element. And then the same situation, from this element to this element, and so on. Everything is clear?
What is the complexity the same? The time complexity?
Yes, the time complexity.
I get it. Still, we needed to be sure.
Mhm.
What is the difference between recursive and hierarchical methods? We find the same.
No difference, just you can write implementation in both ways. And here you shouldn't be afraid of recursive methods because your stack will not be overflowed.
Because we have limits.
Logarithms.
No, I'm talking like we have limit of arrays.
Mm,
Array, and that's why we will not have separate flows.
no, look. So, because in our linear search, our complexity is O(n). That means that if we have million elements, we need to iterate million times. So if we will use recursive method, we will have in our stack million functions. That's why we are getting Stack Overflow. But as this binary search is a lot more efficient, if we have million items, we need some like 20 iterations, so your stack will be okay. So, yeah.
The limit of stack is 1000.
In my case, yes. I don't think that it is a constant number because I think that it.
For each operation, it is different.
I think it depends on your computer, like on the powers of your computer.
Oh, yeah, but I have looked like we have if we do two in the power of 30, we
Mhm.
have 1 billion. So like we have 30 iterations only
Yeah.
for billion. Like
Yeah, that's true, yeah. And it is the worst case scenario, but we can have, we can be more lucky, you know.
yeah, we won't have billion rows or something like that, or billion items in the list.
Yeah, so that's all. Do you have some questions?
No, well, it was very clear. It's understandable to anyone
Thank
who
you.
uses recursive method. Well, it's,
Thank you for your attention, guys.
yeah.
Okay, so let's pay attention to this simple program about binary search. Zoom is preventing me to click the buttons while I'm sharing the screen.
Okay.
Somehow I need to put it away. I just can't click that. Just can't reach. Oh yeah, I need to wait a little bit. So let's start from. Sorry, you don't see my screen, but this screen is very funny because of this button bar. Yeah, I found how to do that. So let's start from, for example, 10 elements. 10 elements and generate array. So we have this array. Let's search something. What do you propose to search? Which element?
66.
66. Okay. Let's go. And we have delay. I will put a very long delay, like 5 seconds, and we will see everything what happening here. So let's just waiting for 5 seconds, and then this is first iteration. The range is all the array. Now then we moved to the second part. Middle is here, then third, middle is here, like, and this is it. This is the end. So we found 5 like index 5. This is our element with 3 iterations. Okay? Yes. Question.
Is it just random numbers?
Yes.
Okay, how do we like do a randomizer with random numbers? With sorted randomizer, right?
Okay. So I created array with random number. Then I'll call method sort in arrays. We have such a method in Java. So we have arrays, and we call sort. And by the way, the sort method implemented. We will learn our next lecture. Vlad will present that in a week. So we will learn about different sort method. One of that method is quicksort. Quicksort, the quickest method to sort. And you will implement it by yourself or with help of many resources, let's say, which is okay. But basically, Java have this method implemented. Here I just call this function, this method. So I get randomized array, then sort it, and after that we could implement our own binary search. Okay. Let's search something else. 30. Okay, let's search 30.
Well, yeah, let's see.
Let's see. Five seconds, yeah. So now middle is this one. Then this part, middle is here. And we get this in 3 iterations, okay? Okay, so what I want you to show that let not now do 100 elements. 100 elements, so how many iterations will we have?
7, I think.
So log of,
Well, we have 64 and 6 and
yeah.
128.
So
and
let's see. So choose what will we search? Maybe if we you know, we could be lucky. It depends of position of the elements, so basically. So what will we search? 500? Okay, let's do it.
Is there a 500?
We have 500, so we could search. So let's make maybe 3 seconds, for example. Now we could make font a little bit less, or even less. So this is our 100 elements. So let's search now. So range from now middle of that, now another part, another part, another part, one more part, finally. 7 iterations, you were right. So we get it in 7 iterations. So before that we had 3 iterations for 10 elements. And just 7 iterations for 100 elements. So we multiplied by 10 our initial data set, but we still have very good numbers. We have just 7 iterations. Come on, it is not just very cheap from performance perspective. So now let's make 1,000. And what will we search? Yeah, you can't see
One.
anything.
Let's search one.
Okay. Any ideas? What do you
One.
want? Just one?
I'm for one.
Okay. By the way, we have no one, but let's search one. Yeah, that would be nice. Okay, so let me make it very small. And let's search. Second iteration, third iteration.
Yeah, it won't be 10 euro. It should be like 9 or 10.
Value not found in 10 iterations. So 10 iterations for 1000. Okay, so remember, we started with 10 elements and had just 3 iterations. Now we have 1000 elements, but we just have 10 iterations. So could you compare that? 10? How? So when this is very like practical example. Why binary search is so important to understand? Because it shows us this complexity stuff. It shows us how much will it grow when our data set grows. So that's why we started with 10 elements, 3 iterations, but 1,000 elements, we have just 10 iterations. So comparing this growth of data set and growth of number of iterations is pretty impressive. That's why it is very cheap. It is very good algorithmic complexity. Let's move to 100,000. And let's search something, what you want to search. So it is many elements here. Very.
Let's do 3.
Let me.
Let's do some large number.
So you could choose any. Do you want to search this element?
Yes. All right, let's go.
Okay.
That's exactly what I wanted to see.
Yeah.
Do it.
Okay. So, yeah. Let me make it very small. Search. Now you see only this gray one because blue list view already can't manage so many items. That's why I use just text decoration with gray. We almost can't see anything, but there is, you see that this gray stuff is showing us that range. Yeah, we see how it works now. Yeah. Value found at index this in 11 iterations. Could you imagine that? We jumped to 100,000 and we have just, we were lucky of course, but we have the iteration just +1. So it is pretty amazing. And let's finish with 1 million. Generate array. And I don't know. So Arsene, what do you think? This one, yeah? 1, 2, 3, 4, 5, 6, 9, 7, 8. Okay. Let's go.
I think we have like an extra 9.
You think? Okay, then we will get -1.
Yeah, that's also good.
So again, because of delays, artificial delays, we kind of wait, but it works. When you have just 10 iterations, it works like millisecond, very quick. On huge data set, it works very.
Let's do no
very
delay,
quick.
like after this.
Yeah, I will eliminate delay. You will see the result. So we have 15 iteration count. We're still waiting. We have this range. 18. One more. Value found at index in 20 iterations. 20 for, and if we eliminate any delays, let me put 1 millisecond and search again. You can't see anything because it is very quick. So let me search for another element, for example, something like that. Brick. Yeah, this is it. 21 iteration. So again, any delays is related to basically visual interface, to this list view, which should be reloaded, and so under the hood a lot of visual work, but the idea is very quick. Like Valentino said, that when you have, this is basic, you will learn databases later. And databases have, one of the common mistake of young programmers, that they create database and they do not create indexes. Indexes, this is exactly what we're talking about. This is sorted part of our data set. We just sort specific column in our table, and we could search by sorted column very easily. And it will be very quick. But if you have no this index, you will have linear search, just what was asked. I know that binary search is very funny. Okay, so this is exactly what will be happened because linear search, you will have million iterations or hundreds, and it will take time, and your users will wait on screen and just waiting for 3 seconds to get results, which is awful basically. For modern software systems, your results should be very quick. That's why you need these indexes, and in that indexes you will use, or databases will use something like binary search, binary tree search. This is very similar algorithms. Okay,